Okay, let's get started now. So hello, I'm Seok-Hyung from Seong University. And before starting, I'd like to thank to the organizers for hosting this wonderful workshop and inviting me as a speaker. So today I'm going to talk about soft output decoding and post-selection for quantum LDPC course, which is about utilizing some additional information besides bare corrections from decoding to minimize the to suppress the resource requirements of quantum error correcting processes. So this work will be mainly based on my recent paper, Efficient Post-Selection for General Quantum LDPC course, which was published in MPJ Quantum Information very recently. And this work is a joint work with Lucas English and Stephen Bartlett from the University of Sydney, where I started this project when I was in the University of Sydney and finished after I moved to Seong University. And since this paper has been released a year ago, and there have been quite a lot of works on soft information decoding and post-selection from that, I will introduce some related subsequent works in the end of my talk. So yeah, so everybody will be familiar with this very well-known challenge of fault tolerance and quantum error correction. So to encode single or a few logical qubits, we need an enormous amount of physical qubits. So for example, for the surface code, for the rotary surface code, when the code distance is d, we need the physical qubit of 2d square minus 1 per logical qubit. So this is the number only for memories. So if we want to do logical operations between multiple logical blocks, we need even more physical qubits, even more logical qubits for that, more physical qubits for that. So to do reliable quantum information processing, this enormous amount of resources is a very important challenge that we need to resolve. And however, our current hardware doesn't have such a capability of including many logical qubits and processing logical operations between them. Therefore, we need some additional techniques for only fault tolerant regime, which is called post-selection. So this post-selection is so the question is, how can we achieve high fidelity with limited resources or with using small codes? So of course, the scalable or the most preferable way might be to increase the code distance. I mean, provided that the physical error rate is under the threshold, we can increase the code distance to achieve an arbitrarily low logical error rate. But in practice, that is impossible because of our current limited hardware constraint. So, so another way is that we use a small code that can be placed on our hardware, but strategically discard computational results with low confidence. So that is after doing quantum error correction, we can estimate how confident our decoding result is based on some information that decoder gives us. And if the confidence is lower than a certain cutoff value, then we can abort the shot instead of abort the shot, which means that just reject the shot error and don't consider it as our main inputs. So the conditional logical error rate, I mean the logical error rate conditioning to a condition on the acceptance could be much lower than the original one that we could achieve without post-selection. And where the post-selection is useful, where one main usage might be the offline resource state generation process. So since the post-selection, since the rejected samples are completely discarded, this post-selection method is not might not be scalable in some sense. So if the circuit depth is, if you apply the post-selection method to our main circuit, then if the circuit is very large, then the overall success rate will diminish exponentially. But if we use this for the resource state generation, even if it fails, so even if it fails to create the resource state successfully, we can still the failure still doesn't affect the main computational circuit. So the many processes in quantum computing utilize the resource state, like for example the well-known magic state distillation, or in general magic state preparation circuits. So by using some resource states and some additional techniques like gate teleportation, we can implement processes that are hard to implement in other ways, like non-Clifford gate. So the crucial part of this post-selection strategy is how we can quantify the confidence of decoding. So the decoding. So the requirement of decoding is that given check measurement outcomes to infer a correction from that counteract noise, where this correction, so in principle, this correction can be logical correction, which logical operation we need to apply. But in practice, we often aim to infer physical level correction. So yeah, and many decoders produce more information than the barrel correction, and we call them soft outputs or soft information. So one representative example of the soft output is the logical gap, or commonly known as complementary gap. So the concept of this complementary gap is actually very simple. So we first run a regular decoder, where let's say it is the minimum perfect matching decoder on the surface code. So we run the MWPM decoder on the surface code and then obtain the primary correction, which is by definition the minimum wave solution or maximum likelihood solution if we ignore corollary letters. But to calculate the logical gap, we need another factor, the complementary correction, which is the minimum weight correction in an alternative logical class, which is inequivalent to the original primary correction, which I denote E tilde. Yeah. So simply, for example, in the case of surface code, let's say these two stabilizers are violated, then the primary corrections could be these two. These are for the simple bit flip cases. So the primary correction could be just these two accelerators, and the complementary correction is composed of these three accelerators. And the logical gap of complementary.
So I guess the first solution can be easily obtained by just running minimum weight perfect matching. So given this solution, how can you get this complementary correction?
Yeah, that's a very good question. So to do that, we need additional defects, additional detectors, additional checks for the logical constraint. So in the case of surface code, it is very simple. We just add one additional boundary check. So yeah, maybe I need to add the figure here. So there could be one bound. So where this boundary check was originally exist in the matching graph of the surface code. So there is an additional boundary graph, and then this boundary check, and this is connected with these 5 boundary nodes. And by assigning a specific value to this boundary check, we can fix the logical class. Yeah. So I will explain it in a more general language in later slides. Yeah. So for the surface code, so we can do that. And yeah, and the logical gap or the complementary gap is defined as the difference between these two log likelihood ratio, LR weight. So yeah, in this case, it will be like this. Now, let's consider generalizing this logical gap, the concept of this logical gap to arbitrary decoders and codes. To do that, let's first mathematically formalize the decoding problem. So the decoding problem can be identified by the parity check matrix, where each row corresponds to an individual error mechanisms, which means that the noise model is like an individual error mechanism occurs with the probability of this probability, each element of this probability vector. And each row of the parity check matrix corresponds to the checks, or where also like termed as detectors in circular noise model. So yeah, and we additionally need an action vector. So this action vector, action matrix. So this action matrix characterize the logical effects of elementary errors. I mean, how the elementary error effect affect the logical observables in the code or in the circuit. And here the K is the number of logical observables here. Yeah, any questions? So like, feel free to interrupt me anytime if you have questions.
So here it's at the circuit noise level or the code capacity level?
It doesn't matter. So it is just general descriptions for all the.
Well, what does it mean by action? Like elementary error, if some detector difference, logical observable is not those local detectors, it's more of a global thing. So how can we prescribe?
So in the case of the code capacity noise model, the definition of action matrix is trivial. It's just the logical Pauli operators of the code.
Okay.
And for the circuit level noise model, it is just equal to the observable in the steam circuit. So like, so yeah. So the action matrix characterize, we can think like after the action matrix characterize the logical effects of errors if we don't decode, if we don't correct the errors. And a decoding instance, so it is different from the decoding problem. The decoding problem is identified a certain circuit and noise model. And a decoding instance is a specific problem a specific instance that we want to decode. And it is characterized by, first, the syndrome data, an observed syndrome, which is a vector of dimension n. I mean, binary vector. Here, m was the number of checks. So, yeah. And we also have fourth configuration that we cannot observe. And this can be denoted as a vector, as an n-dimensional binary vector. But this vector, since we observe the syndrome sigma, this means that this sigma f and the parity check matrix satisfies this relation. And we can also define the logical class that the f vector belongs to by multiplying the A matrix and F vector, which is the vector which is a binary K dimensional vector. And let's also denote the set of errors that belongs to the logical class, which satisfy both conditions. The action should be the logical action by the fourth should be lambda, a binary vector, and also the syndrome flipped by the syndrome pattern affected by the errors is characterized by the vector sigma. Yeah, and by defining the decoding problem and instance like this, the minimum requirement of a decoder is to predict a logical class. So we can like think of a certain algorithm that like all of these are inputs, the H matrix, P, A, sigma, where we cannot use F. F is unobserved. So using these these arguments, we can construct a certain function that returns a logical class lambda. Then if that lambda is equal to the action by the actual force, then we call that the decoder succeeds. However, in practice, most decoder returns a physical correction, not logical class. So the conventional formulation of decoder is to return a correction, which is an n-dimensional binary vector, such that it is compatible with, it is consistent with the syndrome. And we say the decoder succeeds if and only if the marginal action by the residual error. I mean, so the error of f already occurs, and we additionally applied the correction E, then we can call the E plus F as the residual errors. So if the residual error, the logical action of the residual error is 0, then we call that the decoder succeeds. And you can easily see that this satisfies this one. Yeah. So the upper one doesn't require us to estimate the errors. Yeah. No, that is not required. So it is just imagine it's just a function of this parity check matrix, probability vector, action matrix, where we might not need action matrix. Anyway, so since we know that, let's assume that we know that. So HPA, sigma, given these 4 arguments, so it is a function that returns a certain binary vector directly. And of course, we can use an intermediate like E vector there, but that is not required in the bare minimum requirement of a decoder. So the degenerate maximum likelihood decoder is in that case, And another factor is that if we know this, if we determine this lambda, it's very trivial to choose any one of the error that satisfies that it locates inside that logical class. So let's move on. So what we want to do ideally is that first, let's say a decoding instance is given HPA sigma with an unknown fourth vector F vector. Because it is unknown, let's just treat it as a priority distribution, like this Bernoulli distribution. I mean, independent Bernoulli distributions of where each of the element of F is flipped by F is 1 with the priority of Pi. So F is in the logical class lambda with priority this one. So where the syndrome constraint is met, conditioning assuming that the syndrome constraint has met, the priority of the logical actions is equal to lambda. And let's just simply denote it as this notation, just priority lambda condition on the sigma. And the optimal decoder or a degenerate quantum maximum likelihood decoder is often, it can be defined as a decoder that choose the logical class lambda that maximize this priority, this conditional priority. So simply speaking, it is just the decoder that returns the most likely logical class. Assuming that these independent noise models. And the optimal logical gap or optimal complementary gap can be defined as the difference between log of these two values. And here, lambda best is just this one, the logical class selected by the optimal decoder. And this lambda second best is just the logical class with the next highest conditional priority. And this value, this metric quantifies how well separated the selected logical class from the next best logical class. So intuitively, we can use it as a kind of a confidence metric about the of the logical class we choose. Yeah, any questions so far? Yeah. However, although we really want to do this, the problem is that it's very difficult to calculate this conditional priority for all the all the logical classes. Yeah. No, it's okay.
Maybe you're gonna answer this now, but
Yeah.
so the best you can get what's the tensor network contraction.
That's right. Yeah.
And so
Yeah.
you get the second best by contracting a different tensor network.
I'm not sure about that. So I'm not sure how to get that. So I'm not like an expert in tensor network decoder. Can we calculate the coset priority of all the logical classes by tensor network decoder? Yes, we can. Yeah. Then after doing that, we can just simply get the logical gap.
I think tensor network is same as this one with the problem.
I think the certain tensor network that you contract that returns the numbers. So like you contract exactly.
Yeah. So it explicitly gives the logical coset priorities, and then we can calculate the gap.
But that's a 2D tensor network.
It's whatever dimension
Oh,
the
yeah.
code is, kind of. It's like I'm sure
So actually to get it, then you do like multi-parallel sampling.
One code, like
You can do multi-parallel or you can just contract.
Yeah. So let's consider how we can approximate the ideal logical gap. Yeah. So let's first define the weight or log likelihood ratio weight of a fourth vector by this one, which is a very just a common notation of where in weight the weight of an error weighted by the log likelihood ratio of individual error mechanisms. And we can easily see that the priority that this F error actually occurs can be written as this function this formula, which is proportional to the exponential of minus weight. And the coset priority, the logical class priority, can be calculated by summing over all the error configurations inside the logical class. So we can just summing over all the elements in this set, where to remind this set is defined as this set, like the set of fourth vector satisfying the syndrome constraint and the logical constraint. And since this is proportional to this one, we can just get this formula, just summing over all the exponential minus weight. So we can just substitute it to the definition of the ideal logical gap. The optimal logical gap is just the difference between these two log functions, where the only difference is this logical class. This is the lambda best, this is the lambda second best. However, as we have already discussed, it will be very difficult to compute this ideal optimal logical gap. So the key idea for approximation is for each logical class lambda, pick one error vector, then replace this term with the constant vector multiplied by the exponential of minus weight of that. So it is the key idea. So what justifies this one? First, there could be several assumptions which makes this assumption valid. So first, in this summation, there should be a single dominant term which corresponds to the maximum likelihood error that makes all the other terms negligible. And second, we could always find such maximum likelihood correction here. So this like if this error is the maximum likely, then this replacement would be more valid. And third, this constant factor means that the entropy term, I mean, the number of such maximum likelihood errors should be not that hugely different between logical classes. But because we will apply log function here, the condition will be slightly less strict because this constant term will be just moved to log constant. So effectively, the log of this constant factor should be similar to the logical classes. If those conditions met, we can just simply define the approximated logical gap as the difference between weight of these two. So if you are already familiar with the logical gap, this might be a more familiar definition of the logical gap, especially for the minimally perfect matching decoder. But strictly speaking, the ideal version of the logical gap should be defined in terms of the logical concept priority, and this logical gap for the minimally perfect matching decoder or MLD decoder is just the approximated version of that. Yeah. So let's then see how we can obtain this approximated logical gap, just the weight difference between the best correction and the next best correction in an alternative logical class. Now let's again suppose that a decoding instance is given with an unknown fault configuration, and a decoder is also given. We want to use a certain decoder. Now let's define a term decoding within a logical class, which means just decoding by fixing a logical class. And we already have done similar things for the surface code by adding a boundary vertex. To do that, we first define an augmented parity check matrix by combining the parity check matrix and the action matrix, which essentially means that we treat the logical actions as constraint. Yeah. And we also consider the augmented syndrome by adding the by combining the sigma vector and a certain lambda vector. So this augmented syndrome is a function of the lambda, the binary vector lambda. And to decode within a logical class, we run the decoder on this parity check matrix, this augmented parity check matrix and syndrome, like this, to find this fault vector E lambda. So by the way, this decoder we need the second definition of the decoder in this sense, the practical decoder. I mean, the decoder that returns the actual correction. And yeah, and we consider multiple different logical classes. We need to repeat this decoding within a logical class multiple times. So iterating through all logical classes, we decode within each of them and obtain this one. And this lambda prime, we have there is 2 to the k possible logical classes. So we need to repeat 2 to the k times to calculate this. And simply we return the correction that minimizes the weight. And the generalized logical gap is defined as the difference between the two minimum, the minimum weight among these corrections and the next minimum weight. Yeah. So after we calculate this logical gap, the post-selection strategy is very simple. After calculating the logical gap, we just accept if the logical gap is above a certain threshold, a certain cutoff value, and above otherwise, assuming that this logical gap well represents the confidence of the decoding outcome.
One
Yeah.
question. So when you're using optimal decoder from versus suboptimal decoder, does logical gap generically decrease?
Oh,
Is there some monotonicity of this logical gap?
I don't think so. So the individual weight would be, of course, increases compared to the wait. Let me see. Yeah. So even if all the error, or even if the maximum likelihood correction is dominant, still there is the entropy term. So like if I'm not sure if there is a known like relations between the number of most likely errors inside the best logical class and the next best logical class. So they can one can be larger than the other one, and I think there is no strict like relate. Yeah.
I'm asking this because if we use an optimal decoder, then based on this logical gap, okay, as you said, if the delta is smaller than certain constant, then if we just abort, then we can establish some rigorous inequality on it. But like if now our decoder itself is kind of suboptimal, can we still establish this?
So if the decoder is
distance-based kind of some like post selection advantage.
So it is a bit sort of to define the post-selection advantage. So like if we consider like fixing the cutoff value and quantify the performance by the conditional logical error rate, I'm not sure whether the suboptimal decoder always gives the worse result than the optimal decoder. But I think the fairer way to compare multiple different post-select strategies is to plot the logical error rate against the abort rate, not the fixed cutoff value. Then in that sense, the optimal decoder will always give the better results than the suboptimal decoder. I haven't proved that, but I think it might be not that difficult. Yeah.
You're scared of the exponential cost of K.
Yeah.
You could consider like just maybe sampling over the logical classes and like, okay, I'm going to check polynomially many of them, and if any of them have a small logical gap, then I'll post select. So that'll at least help you. Do you think that strategy would be successful? Or?
Yeah, that's a very good question, and I tested that partially in my work, but it wasn't that successful. Yeah, sure. But there could be some more rooms to improve, I guess. So there might be some very good strategy to consider only a polynomial number of logical classes. I will introduce some recent work from IBM about like fixed forced gap, which partially use that idea to optimize the strategy. So now let's talk about the limit. What makes this gap method ineffective? The first one is that the method is valid, as I mentioned, the method is valid when this weight information well represents the likelihood of the logical class. And so this substitution was the key idea of this approximated logical gap. And that is of course non-trivial, not trivial error. So we can't ensure that this is held in general. So if the maximum likelihood decoder is used, then we can, of course, even if it is not degenerate, we can ensure a certain amount of confidence on the approximated logical gap, but still otherwise, so that this statement might be generally not true. So it may underestimate the likelihood of the logical class. And the second limitation is that some decoders may not be suitable for fixed logical class decoding. Because the fixed logical class decoding was done with this augmented parity check matrix by constructed by combining the check matrix with the action matrix. And because this action matrix may contain very high density rows, it might be not compatible with some quantum LDPC code decoders. So I haven't, as far as I know, there are no known like work like quantitatively like compare different strategies on it. But at least for the clustering-based decoders, we conjecture that these clustering-based decoders are not that compatible with this logical gap method because these additional rows will make clusters growing abnormally fast when a cluster meets that additional rows, additional checks. We also call them virtual checks anyway. Yeah. And these two limitations don't apply to minimally perfect matching. So the logical gap for the matching, minimally perfect matching, very widely known, is very known to produce a very effective post-selection strategy for with the logical gap, but in general, it might be not. The second one is, of course, the exponential computational cost. We need to run the decoder to decay time, where this large K is different from the number of logical K here, the number of logical qubits here. So in general, it can be at most 2K, considering both X and Z Paulis. But depending on the circuits, so for example, if we consider memory Z circuits, then logical Z errors will not affect the circuit effectively. So yeah, so in such cases, we can reduce the number of the number of logical constraints smaller than 2K. And this number is very high. Like for the bivariate bicycle code, at most there could be 17 million logical classes. And even if we consider single Pauli memory circuit, we still need 4,096 logical classes. So we need to run decoders in each of them. Of course, they can be parallelized. We can use like 17 million CPU cores to run them in parallel and do that. But yeah. So the goal of my project was to suggest an alternative post-selection strategy that is computationally efficient and applicable to general quantum LDPC codes. So actually, I took a lot of time to explain the backgrounds. Just where one reason might be our strategy itself is not that theoretically justifiable. It's just some heuristics. So I wanted to share the theoretical insights more than that. So yeah. So to define, there could be lots of like different types of decoders for quantum LDPC codes. But what we specifically considered is the clustering-based decoders, which are run by determining valid clusters. Here, valid clusters means some connected set of error mechanisms that contains a local solution consistent with the check adjacent to such clusters. So we first determine such valid clusters and identifies errors in each cluster. So a very well-known example is the union find decoder. And for qLDPC codes, there are some well-known solutions like BPRSD or ambiguity clustering. And we specifically consider the BPRSD decoder in this work. And importantly, this BPRSD or ambiguity clustering is applicable to general quantum LDPC codes. So and another intuition was that these clustering-based decoders gives information on cluster statistics besides the final correction. So we thought that these cluster structures could be very useful soft outputs that can be used for post-selection. Yeah, our intuition was very simple. Just like small, sparse, and isolated clusters means that it is easy to correct. if the clusters are large, complex, and expanding over order lattices, then it might be difficult to correct. So there is no further like theoretical justifications beyond that. So it's just based on these simple intuitions. And we use this, so we can use the cluster statistics to define the heuristic confidence matrix. And what we define these two families of metrics, where this CI is the subset of error mechanisms inside corresponding to each cluster. Yeah. And the cluster size alpha norm fraction is defined by the generalized alpha norm of the cluster size vector. So this is just the size of each cluster, and yeah, divided by just the total number of error mechanisms. So it is between 0 and 1. And if alpha is equal to 1, it is just the total, the summation of the sizes of the clusters. And the cluster error alpha norm fraction is just a weighted version of that. The clusters, the cluster size fraction weighted by the error of each error mechanisms. And our intuition in the previous slide shows that it might be the fact that higher cluster size or error norm fraction means lower confidence. Yeah. And here, by the way, the alpha vector controls the metric sensitivity to the largest cluster. So we don't suggest a certain optimal strategy to find the alpha, but it just needs to be optimized for individual cause and circuits or noise models. So here are some performance measures. So for the surface cause, first these figures, each of these figures shows the logical error rate. I mean the conditional logical error rate after post selection. It is not the logical error rate per round. It is the total logical error rate of D rounds, and against the abort rate by the post selection. So, and we consider three different error rate regime: the 0.1%, 0.3%, 5%. And yeah, and for the surface code, for both the top figures are for the surface code, and these three are for the bivariate bicycle code. I mean for these two variants, 72 qubits and 144 qubits. Where this might give some well, one statement we want to highlight is that for the BB code, for the gross code at the physical error rate of 0.1%, by through the 1% of abort rate per 12 rounds, we can reduce the logical error rate by 1,000 times. So yeah.
This abort rate is controlled by the cutoff that you put. Right?
Yeah, that's right. So both the abort rate and the logical error rate is controlled are the function of the cutoff values. But we thought that the cutoff value is themselves don't give a specific physical meaning. So the important is the tendency of between these two. Yeah.
How many shots of experiment did you do?
Yeah.
I'm just wondering how long does it take to simulate all of them?
As I remember, I did around 10 to the 9. So it depends on the. So I mean, so we don't need to calculate per cutoff. Yeah, the cutoff value can be post-processed after that, and for each of the shots, we're somewhere between 10 to the 6 and 10 to the 9, depending on the code parameters and noises. Yeah, but at least the logical error rate times 10, around that. Yeah, and these error bands indicate 95% confidence intervals. Yeah, so I think so it implies that for example, let's compare the 72 and 144 BB cores. Then it means that if we can abort around 1% from the or 1% per 6 rounds of the 72 with the 72 qubit BB code, we can achieve the same logical error rate as the 144 BB codes without post selection. So it might be not fair directly compare them. I mean, it might be not fair to directly compare different codes with different logical different number of rounds, but that just wanted to like emphasize that the post selection can be useful when we have a limited number of physical qubits. It can effectively increase the code distance at the cost of some non-determinism. Yeah, and comparing with other methods, we considered 2 types of gaps. The first one is the minimum perfect matching decoder, which we only use for the surface codes. And the second one is the logical gap for the BPLSD. I mean, the exhaustive BPLSD, which we only considered for the surface codes as well, because we only have 2 logical classes in that case. But for the BB code case, since we have 4096 logical classes to consider, it is very computationally costly to do exhaustive logical gap calculation. So instead of that, we use a subset of classes for approximating the logical gap, and we call that gap proxy. And for this gap proxy, our strategy was very simple in this case. We just first run the decoder once to get the default class, which is just the basic class with the initial decoding run, and then randomly select other n class -1 logical classes and decode within them and compare them. I'm going to tell a little bit more about this random selection strategy in some of the later slides. And it shows that the gap proxy, so like for the BB code, the gap proxy method doesn't perform well at all. It's just barely, almost similar to the correction weight method. This correction weight method is just post selecting based on the weight of the correction. Yeah. Still, our clustering based method could achieve way more better, lower logical error rate than other baseline methods.
So here, this clustering based method is applicable only for BB code, or what kinds of
so we tested for BB and hypergraph protocol in our work, but in principle, it can be applied to any code. But we haven't checked that they perform well besides this BB and HTTP code. Yeah.
So for the other HTTP code, what's the performance enhancement here? It's like 1033.
Yeah. So they might be in the appendix. I will show you later. Yeah. It's just a similar performance separation. I'm not sure about high rate code. So this is for the LDPC code. Yeah.
Why is this minimum weight perfect matching so good?
Oh, you mean the gap for minimum perfect matching?
Sure.
Yeah. So there was the key idea was that whether the weight of the correction we get represents the likelihood of the logical class. To meet that condition, so I'm not sure about that. I'm not sure whether there are some quantitative analysis on that, but for each logical class, first, the minimum perfect matching decoder works well, even if we add additional virtual boundaries. I mean, additional virtual checks. And second one is that the constant factor, the log of the constant factor might be not that different between logical classes for the surface code cases. I'm not very sure about that. And the third factor is that the minimum, we can guarantee that we can get the maximum likely errors, I mean the minimum value of ways inside each logical class, so that can well represent the likelihood of that class. So yeah, combining those 3 factors, this logical gap for minimum perfect matching is known to show very high suppression rate, like compared to other methods, like more than 1,000 times. Yeah, so our strategy is not we didn't mean to compete with the logical gap. We just wanted to construct a strategy that can be applied to an arbitrary quantum LDPC code. Yeah, some additional analysis on the logical gap proxy. So we tested several different strategies. So with additional information, like we pre-compute the logical error distribution, which is the distribution of this binary vector, and then try to find some better strategy than the random selection, but we failed to find. We just, interestingly, the random selection strategy was the best. So there might be some better ways for it, so we're not very sure. And yeah, time is running out, so let's be quick. So and next, we wanted to extend our strategy to real-time decoding. So we need to decode in real time for practical quantum computing because of one main reason is that we need to do non-Clifford gate, which needs immediate Clifford feedback. So we need to decode before the Clifford feedback is applied. And the second reason might be if the circuit is very long. This might be not a very big problem if the offline decoding is possible. Well, anyway, so we need to do real-time decoding. And a representative method for real-time decoding is to use the sliding window method. Like we divide the decoding problem into multiple windows like this, multiple overlapping windows, and then we decode each of them and commit some first few rounds, and then move the windows and decode again and repeat this until the end of the circuit. So, and there can be multiple options to extend the clustering-based strategy to the real-time decoding, to the sliding window decoding. And we tested several of them, but the one that we finally selected was to first run the decoder in the window, and then choose a certain evaluation region starting from the committee region, starting from a certain past round and the final round of the committee region, and compute the confidence metric, cluster metrics inside this evaluation region. And whenever the calculated metric is above the cutoff, we immediately abort. So that's the big difference from the global strategy. We immediately abort when the abortion when this condition is met. And the performance is so unlike in one of my previous slides, here the vertical axis is the logical error rate, but the horizontal axis is not the abort rate, but the average time cost per accepted shot, which intuitively means that how many. So assuming that we repeat until succeed, how many rounds we need on average to get one effective shot. So for global strategy, it is just 1/abort rate. But for the real-time strategy, since we have intermediate abortion, this is more. We thought this is a better metric. So we showed that these dashed lines are for the global strategy, and the sliding window method, the real-time variant of our strategy, shows similar or better performance than better post-selection performance than the global strategy in terms of these metrics. And we also showed the tendency against the number of rounds. So we showed that the strategy has a very consistent logical error rate and abort rate per round. So of course the constant abort rate. So this is the logical error rate per round. So this is almost constant along the number of rounds, and for the abort rate, it decreases exponentially. So that is unavoidable. So eventually the abort rate will decrease exponentially, and the code. So it is not scalable in that sense. Yeah. But still, since the abort rate decreases consistently, in the log scale, we can at least easily estimate the birth rate for long circuit depths. Yeah, to summarize our work, the post-selection is a powerful technique that can achieve low error rates at the cost of some non-determinism, which can be particularly useful for offline resource generation. And the logical gap method has a very strong like theoretical backgrounds. So backgrounds we can if certain conditions are met, but it lacks computational efficiency and generalizability beyond maximum likelihood decoder. So we introduced another heuristic like framework for applying the post-selection strategy to arbitrary quantum LDPC codes. So where it can be applied to general codes with clustering-based decoders and shows drastic logical error rate reduction. Like for BB code, for the gross code, by averting 1%, we can reduce the logical error rate by 1,000 times. And it can be easily adapted to the real-time decoding. Yeah, and it is open source in GitHub. And let me briefly introduce some recent subsequent works. So since this work has been released on arXiv, there have been quite a lot of works covering similar topics. So among them, there were two representative like post-selections that directly like covers post-selection strategies for quantum LDPC codes. The first one is from China and Japan, and the second one is from IBM and MIT. So yeah, for the first one, it is called the argument reweighting method. So their idea was that we its idea is very simple. We decode once and then reweight errors that are contained that are included in the correction. I mean, increase the prior error rate of error mechanisms, including in the correction, and then decode again. So yeah, so visually it looks like this, supposing that each line corresponds to the likelihood of the logical classes. So we first run a decoder and obtain this one, and and after reweighting the prior error rates, we check whether the new correction is in the same logical class as the first one. If they are the same, we accept the shot. If not, abort. So it is a very simple strategy and is applicable to arbitrary decoders. Yeah, arbitrary codes and decoders. And the second one was released very recently, just on May, and it's very like. Yeah, so it is very, it runs comparative decoding like I described, but instead of fixing all logical bits, so in my previous definition, we consider the augmented parity check matrix by combining the original one and the action matrix, but here they fix only one logical bit per iteration. So it requires only 2K, K+1 classes instead of 2 to the K classes. So I thought of that idea when we did the work, but just naively thought that it might not work well. But they showed that this method indeed works very well for their relay BP decoder. They call it the first gap method here. And here are some performance like comparison between them. So it means that when the abort rate is this value, how much the logical error rate will be suppressed compared to the baseline, or compared to the no post-selection case. So the clustering method, when the abort rate is 1%, the clustering method shows the worst performance between these three. And as I said, the argument reweighting method is applicable to different strategies. So they show different decoders, so they show different performance between them and the first gap method. However, for larger rate, we showed that the clustering-based method still shows some advantage over some other methods. Yeah, these other two methods. Yeah.
So what's the relationship?
Sorry, can you still look? So the abort rate is determined by the threshold. You mean so by threshold you mean the cutoff value? Yeah. Of so that determines the abort rate. So the abort rate is the fraction of samples that satisfy that where the confidence value is below the cutoff value or above the cutoff value. Yeah. 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 So there might be one figure somewhere. Maybe I forgot. Yeah. No, not this one, maybe. Oh. Yeah, I even put this on figure on here, but it is not that simple. So I mean the tendency is like it yeah, I'll show you later. Yeah. Sorry. Yeah.
So in this recent paper by Michael Beveland on this fail-safe, I mean, the fact that so right now you're demonstrating the performance enhancement of post-selection for, I would say, somewhat large error rate regime in some sense.
Yeah.
But when we go to the very low physical error rate, where the logical error rate is now like also like much lower.
Yeah.
Do you think this enhancement for small abort rate would still be observed, or is it that like intermediate region behavior of this like error correction? Do you see what I mean?
You mean?
Because for example, like for the low like a noise regime, not low, but like for large physical noise regime. What I mean large is already like 10 to the minus 2 or 3. Exhibited distance is larger than actual distance, but as p is getting smaller and smaller, where the logical error rate is getting below 10 to the minus 10, now the asymptotic behavior approaches the delta distance, and I'm not sure whether this the post-selection method will still work.
So
maybe you don't need to go further down the regime if you use this method.
Yeah. So at least the logical gap method is more effective when we have lower error rate regimes, because the most likely error will be more dominant in that case compared to high error rate regime. But in general, I mean, this kind of approximated like heuristic metrics, we are not sure. So that need to be checked. Yeah. So whether these methods show similar properties as the logical gap, and at least for the clustering-based method, we partially check that the method is effective when the error rate is small, like numerically, I mean. So these are for, let's see this one. These are for 0.1%, 3%, 5%. So for 0.1%, it shows a very steep curve here. But for these two, it shows very So just we have some numerical results, but not very sure how it behaves. Yeah. Yeah, it's almost ended. So let me just finalize with this slide. So I wanted to emphasize that this field of decoder, these topics of decoder soft outputs have been very very trending recently. So for 1 year, almost 1 year, there have been quite a lot of papers released, including the 3 papers I introduced. There have been quite a lot of papers about post-selection, and we can also utilize the soft information to another use case. For example, there was a very interesting paper on decoder switching algorithm, which means that we first run a fast but less accurate decoder first, estimate this confidence, and then if the confidence is low, we decode again with a slower but more accurate decoder. So proposed by a Japanese group. and similar follow work. And these two are very recently released paper like about adaptive window selection. So the size of the window, sliding window decoding can be adaptively chosen by using the soft information in the decoder. And the last one is about quantum error mitigation and expectation value estimation. So although I mentioned that the post-select, the logical gap method, I mean, the soft information decoding could be useful for offline visual state generation, it might be still like useful for like shallow circuit, like circuits for shallow, some algorithms for using shallow circuits, and with some quantum error mitigation technique. So in that context, there have been several works on that, how we can utilize the logical information for quantum error mitigation, logical level quantum error mitigation. Yeah. So this is the end of my talk. Thanks for listening. Yeah.
Well, thanks, Seok-Hyung. About this point on proving things about the clustering selection, do you have some code property like confinement or soundness?
Confinement.
Distance. Yeah, you have this like confinement or soundness property in code that relates to the error. Have a property like that? Can you?
Yeah, that's a good point. I'm not sure, but yeah, it might be. So we considered several different ways of like theoretically justifying the clustering-based decoders. So like it is not very difficult to construct a very naive bounds with the logical gap and the clustering-based cluster statistics, but that bounds was very not tight at all. So we wanted to find some better arguments on that. I'm not very sure. Yeah, maybe there might be. Yeah.
In your like numerics, you found that it works better on like an qLDPC code that.
Yeah, that's a good point. And I forgot to mention that. So it seems our method is more effective for PV code than the surface code.
So that's gonna have like really low.
Yeah, where their error rate is different, so it might be it is not a fair comparison. But if we, like see the where comparing the surface code under 0.1% and this 0.1%, it seems the performance for the PV code is slightly better than the surface code. But we haven't checked fully of whether it is related to, for example, like degree of the tenor graph and the maximum degree or some other stuff. They might be related, but not very sure. Yeah.
So this clustering method is clustering in the tenor graph, or like for general LDPC code, there's no geometrical property. Then like how what do you mean by clustering?
It's inside the tenor graph. Well, exactly speaking, it is the cluster in the fourth graph, the projection of the tenor graph into the subset of fourth, the fourth node. Yeah. So it is not a geometrical cluster. Yeah. Yeah.
Just wondering, so like optimal, probably the logical error rate is equivalent to complementary gap, right? Just like why you observe is like more like complementary gap dominant, more this is like error in the folder. You can like calculate the complementary gap.
Yeah.
You can calculate the logical error rate, right?
Let me see. That I think that's in the other way. So like if we
the complementary gap basically like characterizes like given the same syndrome, like how different, how likely you were like gave different logical classes, which corresponds to the
no.
Yeah, of course, right.
There can be there might be not strictly so the logical error rate should be the I mean, so given a syndrome, sorry, I'm a bit confused now. Yeah. Yeah.
All the possible,
Yeah.
but
Sorry,
Yeah, just the difference between the two likely ones. Yeah.
Should be the like dominant factor, right? Oh,
That should be the. So I think they have, but it's a different layer, I guess. Yeah. So so there might be strong correlation. So I mean, if we consider something like under fixed syndrome, the logical error rate condition on the fixed syndrome might be very strongly correlated with the confidence the logical gap, I guess. Yeah.
my question is like,
Yeah.
can you like reverse engineer like you analyze suppress error rate to like some say at the -8, and then like can you like derive like you just said that threshold thing?
I'm not sure it might be related, but that approach, I mean, using soft information to characterize the logical noise has been widely studied recently in the context of error mitigation. So for quantum error mitigation, we need a very good noise characterization methods, and this logical information, this soft information can do that. So yeah, I'm not sure if it's related, but yeah. Yeah.
That's the thing.
Sorry, can you say it again, your last sentence? Yeah. Maybe we need mic. Yeah. Yeah. Thank you.
So on that figure A, green result, is that I feel like it might be just because decoder is bad to correct the result, and you kind of remove particular failure mode, and you dropped the error rate dropped significantly. Is that the case, or?
So it means that
there may be very small fraction of mode that always fails, and you remove it, and the error rate drops significantly. So it sounds like, if you improve the decoder, you might just remove that. You might just reach to 10 to minus 8.
So yeah, that's right. So the samples that, I mean, the failed samples will be very, very rare in that case. But the problem is how we can identify such rare samples. And the strategy is quantified by, the performance of the strategy is quantified by how much we can like identify such small set. That might be not a trivial task, I guess.
Yeah, so I think, using your metric to improve decoder, that's another interesting.
That's a good question. I haven't thought about that. Yeah. Using,
Well, I don't think that will go down to like 10 to minus 8.
so it has a limitation, but the limitation, it is lower bounded by of course the optimal decoder, but by the fully post-selected logical error rate. Yeah, was that. Yeah.
Okay, more questions? Okay, let's thank the speaker.